So, thanks to the members of Bookworm Club, it is a different experience. So, hopefully, my pedagogical lectures will be useful. So, I have made this talk very pedagogical, and I will give introduction to frustrated magnetism. This is a very vast subject, and it is not possible to cover in a single lecture. And I would say that even in a single journey of any scientist, it is also not possible to cover all the things. So what I did, as of now, I have came across three different areas I worked in three different areas of frustrated magnetism, and I will give the very introductory level aspect of those systems. So part one, we will consider very basic notions of frustration. Mainly, I will show some examples where the triangles appear as a structural unit. For example, triangular lattice, pyrochloride lattice, and carbonyl lattice. And then I will come to the Hollander lattice. This is the lattice where I extensively worked. Part B will be covered a different aspect of frustration, which is known as 2-in, 2-out rule, or sometimes it is called ICE rule also. This systems is realized in many physical systems, for example, water ice, pyrochloride lattice, diamond lattice, etc. And there is also one system called squaric acid system where I worked it. So I will talk about that. Part C is a different classes of model which is known as quantum compass model, which also shows frustrations. After giving a brief introduction to this quantum compass model, I will describe very briefly the Kitai model where I worked. So everything will be very basic introduction. So the main motivation is to introduce the students to few of the new physics, or I would not say new physics, the physical aspect which is not known till now, at least until master degrees. So those aspects will show how these three different kind of systems can manifest. So frustration can give degeneracy of the ground state, and not only that, it can also lead to non-collinear or coplanar magnetism, which is different than normal collinear ferromagnetic and antiferromagnetic behavior. So then I will come how this frustration can govern a correlated phase and can give rise to the spin glass phase. Then what is the role played by Ising spins, XY spins, or Heisenberg spins? Many times, depending upon the systems in consideration, the spins could be have only one angular momentum component, which is basically a classical. It does not have more than one component. It is just a classical and unidirectional vector. It could have a XY spin. That means it can lie only in 2D plane, only having two components of the angular momentum, and thirdly a Heisenberg spin which has three components. Then one aspect of this frustration is called order from disorder mechanism, where, as I said in the first point, that frustration gives rise to degeneracy. That means once the frustration is there, there will be many competing ground states or competing states classically. Now, and very interesting phenomena happens that once we allow quantum fluctuations, all these classical ground states can further minimize or further lower their energy to different extent, and it may happen that some or few of the classical ground state have more power to minimize their energies, and those will be selected as a true ground state. So this mechanism is called order from disorder mechanism. Then I will show how emergent electrodynamics appears in systems with spin ice kind of arrangement that I talked about. and how interesting physical phenomena such as fractionalization, entanglement, quantum spin liquid, all those appears. One by one, I will explain all those things. So fractionalization is a phenomena where sorry, fractionalization is a phenomena where a elementary particle with some quantum number get fractionalized, that means separated into more than one quasi particles or daughter particles or elementary particles. I will talk about that. And this fractionalization phenomena comes due to some quantum aspect which is known as entanglement, and all those things like fractionalization and entanglement are the characteristic properties of quantum spin liquid, which is also a manifestation of frustrated magnetism, and people are working very hard to realize quantum spin liquids. So those fractionalized particles can have braiding properties which is different than fermionic or bosonic exchange statistics. For example, we know if we interchange two fermions, the wave function is -1. If two bosons interchange the wave function, it will be nothing will happen. But for anyons, the phase one exchange phase could be a fractional, anything in between 0 to 2 pi. So these braiding rules I will explain, and then I will briefly describe what is topological order realized in quantum spin liquid. So this is the flowchart of magnetism in short. So firstly, we have a non-magnetic, we have a materials, and then these materials are classified into two. One is magnetic, another is non-magnetic. Then magnetic materials are further classified into two different possibilities. One could be collinear magnetism, another could be non-collinear magnetism. Then non-collinearity can happen in various ways, mainly two, which is coplanar and non-coplanar. The examples are written. Then collinear magnetism can appear into various ways, commensurate and incommensurate. Again, this commensurate collinear magnetism can have two different kind of appearance as far as the underlying crystal symmetries are considered. So something happened that this underlying magnetic ground state is compensated by the crystal structure, then that is called crystal symmetry compensated, which has two main branches, antiferromagnetic and altermagnetic. Otherwise, on the other hand, not crystal symmetry compensated has two branches, which is ferrimagnetic and ferromagnetic. That particular chart appeared very recently in PRX, EPS website, and this appeared just to highlight that recently a new state of magnetic state was discovered, which is known as altermagnetic, and there was a debate whether altermagnet is a new quantum state, magnetic state, or it is some form of combination of ferrimagnet, ferromagnet, or antiferromagnet. Now, consensus is that altermagnet is a new state of matter. So that's why, to stress upon that, this particular flowchart appeared in the APIS. Okay. So basic interactions. So we came across different types of basic interactions like ferromagnetic, antiferromagnetic, and Dionysky-Mourier interactions. We know how they appear. For example, let's start with two-side Hamiltonian, which is HSI.Sj. We know that if the exchange coupling J is greater than 0, this is antiferromagnetic. If J is less than 0, then this is ferromagnetic. In the left side, we have shown the arrangement of spins of two spins having a ferromagnetic arrangement. So they could be both up or they could be both down, as shown by the two red arrows and two blue arrows. For the antiferromagnetic, we know that if one spin is up, other spin could be down. And I would recommend that to go through all those basic properties like Curie-Oasis law, Nil temperature, formula for susceptibilities for ferromagnetic, antiferromagnetic, and paramagnetic. To begin with, we can have a graduate textbook like Ascom and there is I have given a very nice references as a tutorial. One can have a look at that also. A practical material example where all these different well-known magnetic states are realized. So now how it is frustration? So there are two different kind of origin of frustration. First one is called geometrical frustration. So and then second one is a competing ferromagnetic and antiferromagnetic interactions, which is also called competing exchange interactions. And then the third kind of frustration is appears because of direction dependent exchange interactions, which is known as compass model. So the first one, geometrical frustration, I tried to explain here. Probably many students already know it. This is for the student who doesn't know it. So let's consider a triangle and we put classical spins at the vertex of this triangle. We enumerate them by 1, 2, 3, and the Hamiltonian for this triangle is given as the dot product between the nearest neighbor spins. Now, if we demand that is it possible to align the spins such a way that all these three terms in the summations are simultaneously satisfied, we will see that this is never possible. So such a contradictory arrangement has been shown by these three different triangles, and the question mark means the spins in these sides are do not know in which direction to be aligned. Whatever may be their directions, some bonds could be frustrated. That means the exchange interactions that will not be minimized. So then what happens is that anyway we have to put the spins up or down. The moment we put up and down, what will happen that there will be many equivalent configurations having the same energies. For example, for these triangles, we see that there are at least 6 configurations with identical energy. So this is an example to show in a very elementary way that frustration leads to degeneracy. So now this will also happen for other many complicated lattices, complicated spin arrangement, etc., etc., and the consequence of those upon classical or thermal fluctuations is a big question and a very interesting research areas. On the other hand, if there is no frustration, that means if we have a ferromagnetic interactions or all spins could be up or all spins could be down, nothing interesting happens. So once this degeneracy appears due to frustrations, what happens that when we allow thermal fluctuations and quantum fluctuations, all those degenerate ground states compete with each other and can lead to a exotic ground, further new exotic ground state. Okay, so here I want to show how the competing exchange interactions can lead to frustration. So let's consider a square having spins 1, 2, 3, 4, and we can define a antiferromagnetic Hamiltonian as given by this S1.S2, S2.S3, S3.S4, and S4.S1. Okay, so I have in the right side I have shown two equivalent antiferromagnetic arrangement where such that every bonds are minimized. So this is a non-frustrated system, very good. Now H prime denotes a original Hamiltonian H plus S1.S3, that means the spins along the diagonal. S2.S4, that means another diagonal interactions. So if we allow now the antiferromagnetic interactions along the diagonal, we will see that this does not, this competes, or this does not go well with the original spin configuration. For example, in the initial Hamiltonian, the diagonal spins are ferromagnetic as dictated by the original interactions. Now if we put on an antiferromagnetic interactions, those interactions will be not satisfied. So that means frustration arises. So here is an example how the frustration comes due to the competing ferromagnetic and antiferromagnetic interactions. So then what could happen? A geometrical frustration due to competing interactions. So here I have shown a triangle in the right side with a different colors, red, blue and black color. So red color, the spins connected by the red colors, they interact through their x component only, which is written as a H triangle S1x, S2x. Now the two spins connected by YY bonds, they interact only through their Y component, and similarly the black bonds such that the two spins connected by the black bond are connected by the Z bonds, or they interact with Z bonds. So now here also frustration arises in the sense the red bonds will try to align the spins along x directions, but definitely that will not go well with the YY or ZZ interactions, because their component along YY and ZZ is 0 if the spins are already aligned along x directions. So the YY or ZZ bond will not be satisfied. So this also an example of frustration, and this particular frustration is known as compass model. So here at the end I have given the distinction between Ising spins, where only one component of spins is non-zero, other two are zero. Then XY spins, where X and Y both are could be non-zero, Z component is 0, and Heisenberg spins, where X, Y and Z, three components will be all non-zero. So this is a slide to show that how frustrated magnetism can give varieties of ground state. So starting from the ferromagnetic to stripe order to 120-degree needle order to spiral order, the details can be found in this reference paper. This is just an highlight. There are many other materials, other papers to show as we tune on the parameters, the ground state can have many different states. Now I will come to the material IOR, which is known as Hollandrite material and also known as alpha manganese oxide. So let me go quickly how this alpha manganese oxide looks like. So alpha manganese oxide, here it is a tetragonal structure. Inside this blue are the manganese oxide, and it was surrounded by 8 oxygens. There is corner share tetrahedra, and there is edge sharing tetrahedra. Depending upon the edge sharing or the corner sharing, the distance between manganese oxides are different and their exchange couplings are different. So the lattice looks, so if we now remove the oxygens, then the manganese oxide, manganese, they form a lattice which is known as the Hollandrite lattice. So Hollandrite lattice has this kind of tunnel structure. There are two kind of tunnel. One is tunnel by the 8-side tunnel, and there is a small tunnel which is known as the 4-side tunnel. So if we now remove the oxygens and keep the manganese oxide, the resultant lattice looks like this. So here the black dots are the manganese, and there are 3 different kinds of bonds which depending upon the distance we give the color code. So there is a green one, there is a red one, and there is a light blue one. So 3 different kind of exchange coupling we introduce, and the model is written as given by equation 1, which is J1 Si dot Sj plus J2 etc., etc., these things. So ij within angular bracket 1, that means it is connected by the green bond, sorry, light blue. The 2 means red bonds, and ij within angular bracket 3 means red bonds. So this system can be thought of as a interconnected zigzag chains. There has been many experiments on this material late 90s, and what is the ground state or etc. there was not been much work. So we had explored that material, but before that we want to show that if we want to explore, as we see this material, we see that there is always a triangle present. Okay, so this triangle gives rise to the frustration to this Hollandine lattice. This lattice is closely related to other two lattices, which is known as Fisher lattices and 3D triangular lattices or 2D triangular lattices. So I will explain a little bit about that. So this is a one face of this lattice which is given in the panel A. Now here we see that 1, 2, 3, 4, 5, 6, 7, 8. It is an 8-side unit cell. It is in XZ plane. Now think about such planes are connected into the Y directions. Then it will form a 3-dimensional lattice, and that lattice is the Hollandine lattice. These 8-side tunnels, when connected in the Y direction, how does it look like? This is shown in panel B. The tunnel will go like that. In panel C, we have seen how the tunnel looks like. This 4-side tunnel, when does it allow them to repeat in the Y directions? Now, a 2-dimensional plane of this Hollandine lattice is closely connected to the a 2D layer of the triangular lattice. So the right panel, what we have shown is a 2D plane, and which is related to the 2D triangular lattice. So now when we try to explore the magnetism of this Hollandine lattice, it is good to start to explore what happens for a single chain. So if we now consider a single chain like as given here, the red bonds are having interactions J1 and the green bonds are having interactions J2. Now the student can go to their table and find that depending upon the sign of J1 and J2 and depending upon the magnitude of J1 and J2, there are 3 different possibilities of the classical ground states. Among them, the second and third one is very interesting. For example, the second one, we see that the parameters are such that ground state is minus mod J1. That means ground state does not depend upon the value of J2. This is a sign of frustration. And as the ground state doesn't depend upon J1, it has a lot of degeneracies. One need to work it out and then find it out. Similarly, ground state 3 is also frustrated. One need to check it explicitly. Now the question is, if such chains are connected in a certain manner and give rise to Hollandine lattice, what will be the resultant classical ground state? And then if we want to solve it quantum mechanically, what will happen? Those are the questions we are looking for. So here is more details. Explanations has been given how this single chain works. One can go through it and verify it. Okay. Now I want to give the exact solution of this chain. So let's say my Hamiltonian is J1 Si dot Si plus 2. This is the red bonds, and J2 is Si dot Si plus 1. One can say that the blue bonds connect the nearest neighbors, but the red bond connects next to next nearest neighbor. So that's why it is I interacts with I plus 2. There is a well-known method to solve such classical ground state, which is known as Latin-Tija, which basically works upon by Fourier transform it, then finding the minima of these characteristics interaction matrix, and find out the values of k, and then with this k one need to construct the classical ground state for which it can have minima. So what we find is that once one do these exercises, it gives the classical ground state of minus j1 mod minus j2 square by 8 j2. So this extra term was not present for this case of middle choice. So the lesson is that once we allowed classical fluctuations, then the state can further minimize their energy by allowing non-collinear ground state. Here it is the helical ground state, and this particular new energy contribution comes by allowing the classical fluctuations. That means initially we had Ising spins, now we are allowing them to be XY spins. So one more component it can have. And definitely the very much question arises, what happens if we now allow quantum fluctuation? Okay, so here is many references, one can go through it, how this Latin-Tija works in a very complicated systems, the improvement upon Latin-Tija, and references of our work also where we have found an exact interaction matrix method. Okay. So here is a summary of our finding of this classical ground state of Hollander lattice. Let me go through it very quickly, in the sense that what we found is that this phase shows various helical ground state, and this helical spins looks like this in this panel P, where spins rotate in a certain angle. So as we go along the y directions, the spins rotate in a certain angles, but spins are always in a xz plane. So, and in the next y plane, the spins are rotated by a certain angle. So this is the phase diagram of the Hollander lattice in the plane of J2 and J3 exchange couplings normalized by J1. We found 4 different kind of helical ground states and also 4 collinear ground states. Basically, this kind of helical chains, this is a helical chain. These helical chains either parallelly or anti-parallelly connected, and depending upon their mutual orientation, 4 possibilities can appear, which is known as C2H phase, CH phase, A2H phase, and FH phase. For details, I refer to the original work. Okay. So this is a Heisenberg spin result. Now initial work was done by our collaborator, which is by considering the Ising spins, and there was a phase which is known as geometrically frustrated phase, where the energy was only minus J1 independent of J2 and J3, as I explained there. So those geometrically frustrated phase, when Heisenberg interactions were allowed, it gave rise to the helical phase. Interesting one thing to note is that this geometrically frustrated phase was for a very small region, but this helical phase is in a very large region. So that means even the classical fluctuations enabled went to the eaten up some phase boundary of these classical configurations. Sorry, collinear configurations. So there are some lessons and references, one can go through it for further work. Okay, now I come to the physics governed by the ICE rule. So ICE rule, we all know our water when it solidifies, it gives us to the ice. So, but we do not know that depending upon the temperature and the pressure, this ice shows 20 different phases. I will come to the next. How does this? But how does this ice rule works? So we know that it is made up of H2O. So and in ice state, it is in a diamond lattice formation. So the oxygens form a diamond lattice. So here the red dots are the oxygens. Now, a given oxygen is coupled to two hydrogens, which is given by the yellow dots. Now, what happens if you look at some sites, oxygen, it is connected to four other oxygens, and on each bond there are two hydrogens. So it may happen, it just happens that in this case of ice, that two of the hydrogens are nearer to oxygens, and two hydrogens are away from the oxygen. So this two in and two out rule is known as the ice rule. Now, if we say that if we say assign some fictitious charges to these hydrogens, for example, plus, then 2 is closer to the oxygen, that means it is contributing to the plus 2. 2 is away from the oxygen, that is it is contributing minus 2, then the total charge is 0. So in the sense, if we have some measurement or some notion of charges around one oxygen, we'll found that the number of hydrogens are 0. Protons are 0. Hydrogen is equivalent to proton. So this particular rule is known as Gauss law. I will come later. So here is the phase diagram of our ice in different systems and different phases. One can look at these references. Okay, such position of hydrogens are now mapped to a dipole moment or the spin angular momentum. Then it becomes a spin problem, and actually there are other lattices such as pyrochloro lattices or the Kagome lattices, where at a given site four bonds meet together. And exactly we can assign four vectors around for each of this line, and then we can ask what are whether the ice rules are satisfied for this material or not. Actually they does. So if we assign four spins, then these four spins form a ice rules, and this type 3 and type 4 are not ice rules, and these are the picture of artificial materials formed to check whether ice rules are really satisfied in some material. They actually found it. We will show the references later. Okay. Now, if such ice rules are formed where summation of charges are 0, here I have given summation over SI equal to 0. 2 in, 2 out rule. Two vectors are inside, two vectors are going outside of a given volume, then the total vector summation is 0. This is exactly the classical electrodynamics static Gauss law. No charges are there. So this was the point where we started. It happens that the summation over charges equal to 0, that is the Gauss law. If we want to violate it, one cannot violate it for a given site, it has to violate in a pair. So the moment it is violated in a pair, it amounts to creating positive charge and negative charge. So as shown in the right side panel by the red region and the blue region. Once the white color or the various lines connected between the blue and the green are the electromagnetic forces. So once these charges now moves by rearranging the spins, then what happens that magnetic field also arises equivalent. And actually people have calculated the fine structure constant for this kind of emergent electrodynamics also. So there is some references and the history of this, and there are one material that we worked on. I will talk about little bit. So this is this model Hamiltonian for the squaric acid systems. Here the square object, black square object with 4 arms is the C2O4 element, and these red dots are the hydrogens or protons. So as you see that one protons is always moves in between two oxygens. So as if there is a two double well potential and it moves between those. Its position relative to two double well potential give rise to two positions or the two spin component like +1 plus Z or minus Z. So the Hamiltonian is little bit complicated. Let's do not go in details. So at zeroth order we have a 4 spin interactions, and then we have an Zeeman field also. Then there is nearest neighbor coupling also, and there is a dipole-dipole interactions also. So now the question is, once these interactions are allowed, what will happen? At the zeroth order, the J0 term, as we see, this S1, S1, S2, S3, S4, the 4 spins in a square are product, then the classical ground state are such that their products are always +1. So in this panel IV, these 8 configurations are possible where their product are all plus. So as you see, among these 8, there are 2 choices where all spins could be plus, all spins could be minus. Other cases, other 6 cases, only 2 of them are plus, 2 of them minus. Exactly the ICE rule condition we explain later. So now, in some sense, in the ground state manifold, there is spin configurations where large number of spin configurations follows the ICE rule. Now the questions will come. Actually, quantum ground state, it is very difficult to find. And now if we allow thermal fluctuations, what will be the phase diagram, etc., etc., those are the questions we looked. So there is some phase diagram, very recent work, 2014 PRL paper, where they have found that it can go from deconfinement to the confined phase and some ferroelectric phase in the coordinate system by J1 by J2, where the correlation functions in deconfinement phase follows power law behavior, and in the confined phase goes like exponential. So it is a log plot. So that's why the exponential plot is given by the straight line, and power law is deviated from the straight line. So we did some kind of classical phase diagram. Details is can so the references. What I want to stress out that there was an earlier work by Lee who has calculated the ground state degeneracy for this ICE rule exactly, and it is given by W to the degeneracy is 4/3 to the power 1.5. Now, given these different different parameters in our model, we have found that when J0 is not equal to 0, the ground state degeneracy can be computed as 2 to the power nx ny plus 1. Now we allowed it to be as a quantum fluctuation, and we asked the question whether all those classical ground states can further minimize their energy, and we found that it does not minimize further. So even after allowing the classical configurations or even allowing the quantum fluctuations, all those classical ground states equally minimize their energy. So this is a counter example of order from disorder mechanism, and we found that what is the reason for that. So we have found that there is some loop operator for which it does not happen. So there is a protection from quantum mechanics or symmetry operators which deals all these classical ground state equally even at the quantum level. So the reason is given here. that the last statement is important, that degeneracy persists even after quantum fluctuations are allowed. So this model is we have written in a some particular limit where the Gman term is very less. Kx and ky is very less than the zeroth order term J0. In this limit, this Hamiltonian can be perturbatively calculated, and at fourth order some effective Hamiltonian is defined. I will show that later, that or it is discussed in our paper, that this particular Hamiltonian is known as toric Hamiltonian, and exactly this Hamiltonian has abelian excitation. That means here these two terms, each terms can be thought of as some Hamiltonian for two different particles, and their exchange statistics are different than fermions and bosons. Okay, let's move faster. These are our paper, which is not needed for this pedagogical talk. Yeah, for details, one can go through these references for further work. Okay, now I will come to the last part, which is known as the spin liquid or topological order, or whatever you are discussing, fractionalizations. So as of now, we discussed very extensively the manifestation of mainly the classical description of frustration. Now what will happen at quantum level? So at quantum level, a strong frustration for a two-side leads to a state which is known as a spin singlet, which is a linear combination of up down plus down up. If it is a classical state, either up down or down up will be there, but if it is a quantum, it has to be superposed. Now here in the panel A, we have shown a state where every side is connected with other side by forming a singlet, and they form a nice pattern. Even in panel B, they form a nice pattern, but there is a difference between panel A and panel B. In panel A, I have only one arrangement of the dimers. In panel B, it is a linear superpositions of many such configurations. Panel C, it is further different than A and B. In panel C, the singlets can form between sides which is very a spin away from each other, like given by the light blue or yellowish blue line. So what is the difference between the panel A, panel B and panel C? So panel A, two spins connected by or within a dimer, they are as a quantum mechanical, but it is as if a direct product of such dimers. For panel B, it is a superpositions of such configurations, and this is actually leads to entanglement. In panel C, it is much more exotic in the sense that a spin can form a dimer with another spin which is much away from it, and this is known as the long range entanglement or the topological order, whatever give rise to. So idea of fractionalization example in simple system. So here nowadays we are all know about many heard about many one-dimensional model like SSH model, Kita model, etc. 1D XY model, etc. So let me give the idea of fractionalizations in the context of a very well-known model which is known as Ghose-Mojumdar model. So here the Hamiltonian is same as the one-dimensional chain that we talked about for Hollandite systems, J1 and J2. So J1 is the nearest neighbor interactions and J2 is the next nearest neighbor interactions. And both we consider here is antiferromagnetic. When J2 is half of J1, at that particular point, Ghose-Mojumdar has found, this is our famous Chanchal Majumdar, Professor Chanchal Majumdar, and student. Professor Chanchal Majumdar was the founding director of Asian Wars National Center. So there are two degenerate ground state, which is known as the product of singlet state. So one ground state is given by this configuration of dimers by red lines, red dimers, and then another is the other combinations where the spins form a partner with the left one. So these two equivalent configurations are possible and they are degenerate. Now once we break a dimer, we create an excitation. So these excitations are like two parallel spins. Now what happens is that these two parallel spins are the zeroth order excitations of this Gauss-Majumdar model. Now this is the particle at zeroth order, a single particle or single particle excitations. Now what happens is that these particles with spin s equal to 1 excitations, due to the quantum fluctuations, it's separated into two different particles and they now move independently. This idea is called fractionalization. So now I will briefly describe the Kitai model, and which is an example of the quantum compass model. So Kitai in 2002 had proposed one model which was meant only for practical purposes for topological quantum computations, and we had no idea that this model would be such an interesting research field, and furthermore we had no idea that after 10 years there will be some material where such interactions will be realized. Let me introduce what does this Kitai model is. So in the beginning we have a honeycomb lattice. At the honeycomb lattice, every point we have a spin-up object. Honeycomb lattice is a two sublattices given by the black and the green. Now this honeycomb lattice, we have three different kinds of bonds, which is given by the red, blue and the black. Now if the two spins are connected by a red bonds, we call it an X bond. That means these spins, when connected by red bond, they interact only through their XS component, and this is given by the first term of the Hamiltonian, which is Jx sigma Ix sigma Jx. The second term is given by the blue bonds, where the spins interact through their Y components only, and the vertical bonds are the Z bonds, then they interact through their Z components only. In a short, at a given site, the spin has all the component X, Y and Z, but when it sees a red neighbor, it is allowed to interact through only their X component. When it sees a Y neighbor, it is allowed to interact through their Y component, and when it sees a Z neighbor, it is allowed to interact through their Z neighbor. So one can show that the classical configurations are mutually competing, in the sense if it has to align along X direction completely to maximize the first term, sigma Y and sigma Z component will be 0. So this is a origin of frustration in this case. There is a very interesting work where they have found that if we consider a particular zigzag chain, that means let's consider my Z interactions as 0. I have only X and Y, that means I have only the red, blue, red, blue, red, blue chain. So this is a one-dimensional Kitai model, spin version. And then one can show that there is a family of classical ground states, and now one do quantum fluctuations, one see that only particular state with such a theta equal to 0, pi by 2, pi or 3 pi by 2, those states are the absolute minima. So this particular phenomena is the example of order by disorder phenomena. Now, normally this Hamiltonian of first-state magnetism is not exactly solvable. So it becomes an interacting Hamiltonian, and actually true quantum mechanical solution of such Hamiltonian is a tremendous task. What happened is that Kitaev tried to solve it using some measuron of fermion, and he fermionized it, and due to some particular specific nature of this Hamiltonian, it becomes a product of this 4 measuron of fermion product. Among these 4 measuron of fermion, the two terms within the red brackets, it becomes a conserved quantity. It means that it commutes with the other part of the Hamiltonian, mutually commutes with on every bond. So ultimately, after some algebra, one finds that the Hamiltonian looks like a non-interacting measuron fermion hopping problem. So the Hamiltonian within this square bracket is the final Hamiltonian after measuron fermionization. If you look at each term, it has I, CIA, CJB, which is like one measuron fermion is hopping from site I to site J. Site I belongs to A sublattice, site J belongs to B sublattice. Now this is coupled with a gauge field, which is the U, and these gauge fields could be +1 and -1. Now and these are conserved quantity. There will be a various choices of these conserved quantities. Once these conserved quantities are fixed, then one can solve it by exact diagonalization. One can calculate the ground state, etc. Now, but those ground state energies will be a functional of these conserved quantities or the configurations of conserved quantities. Now the question will come that which configurations of these conserved quantities will give me the exact or the absolute ground state energies. Professor Liev in 1994 has solved that problem for Hamiltonian, reflection symmetric Hamiltonian, and Halnicum lattice is also reflection symmetric, and he has shown that when these gauge fields are such that their product over a honeycomb bracket is 1, that will correspond to the absolute minima. One choice of such is that we choose this uniform gauge field to be uniformly 1, and if we took uniformly 1, then one can do a Fourier transformation and can solve the Hamiltonian. So then one find the dispersion relation given by this, and this dispersion exactly looks like the graphene dispersion. And so in the parameter space of Jx, Jy, and Jz, one finds that let's consider this big triangle and consider any point inside this triangle. The distance of it from any of these three outer triangle is the value of Jx, Jy, and Jz. Now if consider any point, then it will give a set of Jx, Jy, Jz. And we now given a set of Jx, Jy, Jz, we calculate whether it is a gapless or gap. One finds that this region B is gapless phase and the region A is gapped phase. So this region A to B is a topological phase transition in the sense that it is different than Landau phase transitions. In Landau phase transition, for example, solid to liquid, symmetries are changes. In topological phase transition, symmetry remain unchanged. So this is a big differences with this topological phase transition. And this gapless phase B, once we put a magnetic field, it opens up a gap, and one find that the excitations are here non-abelian anions, and in the gap phase these excitations are abelian anions. Details can be found in Kitaev's paper. I think I have given the references of Kitaev. Let me check it. Yeah, this reference is given. Okay, what we have shown that in this Kitaev's model, one can do some exercise of this fermionization procedures, and the effect is shown here. So let's consider this is my ground state, and we apply a spin operator sigma iz. Once you apply a spin operator, this spin operator adds to the ground state two flux excitations, in the meaning that the BP operator, we talked about the product of conserved quantities along a placket, so their value is now changed from +1 to -1, and also it adds one Majorana fermion which is given by the black dot. Now these fluxes are conserved, so once we evolve this state, these fluxes do not move, but this Majorana fermion moves, and this fact is called the fractionalization of spins. So the spins was a physical object, a single object. Now when it acts on the ground state and the ground state is evolved in time, it shows that the action of the spin is such that it decomposes into two different objects. So, and based on this fact, one can show that the spin-spin correlation functions are non-zero only for the nearest neighbor bonds. Also, it is bond dependent, but there is a multi-spin correlation function which is non-zero, and this multi-spin correlation function gives rise to long-range quantum entanglement. So here is a brief introduction about anyons as quasi-particles and its bearing. So normally we know fermion and bosons in 2D and 3 dimensions, but there could be exclusion statistics and exchange statistics, which is different than fermion and bosons. So Professor Halden first introduced the concept of Halden statistics, where the exclusion statistics are different than fermions and bosons. So if we consider bosons, if in some state the other bosons can also occupy that space, that means the possibility of or the power of bosons to completely occupy the state is 0. So that is the statistical parameter G is 0. For fermion, if it occupies some state, other fermion cannot occupy that, so its exclusion statistics parameter is 1. On the other hand, there is exchange parameters which is related to the phase of the wave functions. Now, Professor Murthy and Shankar asked the question whether these two parameters are equivalent or they are connected or not. So they have found that they are connected in some parameter regime which is given by G equals to alpha into 2 minus alpha. One can look at these papers for further. So here the Majorana fermion, there we will see that their braiding really depends upon the path, and as their braiding depends upon the path, it is called non-abelian anyons. Here is a proof of that. One can go through the slides and check the mathematics done here. Yeah, so more details of the mathematics one can go through it. I'll be always there. If any student needs any clarification of these slides, I will explain anytime. Okay, now we come to the braiding of quasi-particles in some limit. When Jz is much larger than Jx and Jy, what happens? The Hamiltonian breaks down into two parts. One and also the honeycomb lattice is mapped to a square lattice. So one is a star operator which is given by these red dots which is connected. So the star operator are product of 4 spins of these 4 bonds coming out from this site. And this placket operator BP is connected to bonds of a square placket. Okay. So these two are one, the star operator includes X component and this includes the Z component. So one can show that they mutually commute. One can find the ground state. The ground state is called loop gas. That means spins can have random orientations, but such a way that it has to find a certain constant along over a loop on the square lattice. One can have excitations and one can create 2 such star operator to be -1. One can have excitation such that 2 of these bracket operators are -1, and one can braid one such star operator along another bracket operator, and one can ask the question, what is the exchange phase? So what happens is that if these 2 star operators are exchanged among themselves, nothing happens. if two placket operators are exchanged among themselves, nothing happens. So mutually they are bosons. But when a star operator is taken across another placket operator, then a phase of -1 comes. It is a very interesting phenomena, and which is known as semions. Now I will show very briefly how this topological degeneracy appears for this model. Apart from these local conserved quantities, there is a long range or global conserved quantities which is known as Wilson loop operators. There are three Wilson loop operators and only two of them are independent, and due to the presence of two independent Wilson loop operator, there is a degeneracy of 4. Details of the proof is given in this paper. One can look at there, and again I am there to help you out for more explanations. Okay. Further proof of this topological degeneracies, which is I think not needed for this pedagogical talk. I will just give briefly our recent work on this Kitaev model in the presence of Heisenberg and gamma interactions, which was motivated by the recent materials. The slide was included due to the fact that this is the Kitaev interaction first term, second term is the Heisenberg interactions, and the third term is the gamma interaction. What we have found that when we plotted the correlation functions as a function of the Heisenberg interactions, we will see that we found certain plateaus, and after some investigation we found these plateaus where correlation function does not change, the ground state wave function does not change, and it becomes very interesting that we have a Hamiltonian and we are changing the Hamiltonian parameter, the ground state wave function is changing, but for some range the ground state is not changing. And a more investigation revealed that for this range where the plateaus are there, the exact ground state becomes the exact eigenstate of the Heisenberg Hamiltonian also. Why this is interesting? In the sense that in Hamiltonian I have different parameters which does not commute with each other, so I should not expect that they will have a mutually same set of eigenstate, but here it appears, it just happens that, and this is a very new phenomena which is we are very happy to find this result, and that's why I included a little bit of that. Further of Majorana dynamics details can be found in this paper, in the sense that where the gauge fermions or the fluxes we talked about, normally the other interactions when we add into the Kitaev fermions, the gauge fermions are no longer conserved, but we have found that if we apply a magnetic field, these gauge fermions can also be made again close to its conserved values. So this could have a further applications or way to explore physics further. So with this I end, and there are lots of references. Any confusions or discussion is needed, anyone can email me or contact me anytime. I will be happy to clarify. So with that I end. Thanks.